Now, we do want to look at one specific variation of this exponential function, right? In the last few problems, we had things like doubling, tripling, half, where the growth factor was explicitly defined. In many cases, your growth will not be expressed as a growth factor, but rather as a rate of change, or in other words, as a percentage. What percent are we growing by? What percent are we decreasing by? So the way we represent percentage, rate of change in this case, is we replace our b value with a 1 plus, or if it's decreasing, 1 minus this rate. Now, when we're working with rates, although we're given it in percentages, we're going to be working in terms of decimals. Okay, so everything's converted to a decimal. So a to the t, right, the amount after t time periods with an initial amount, we will replace the b with 1 plus or minus r. We add r if it is growth. We subtract r if it is decay. And the exponent is still the number of time periods. So, for example, let's say we are increasing by 20%. Okay, what is my b value? What is my growth factor? Well, think of it this way. We want the original 100 and then an additional 20%. Right, 100% is the total plus an additional 20%. If I express this as decimals, right, 100% is equal to 1 plus 0.2. So my growth factor here will be 1.02. So your equation will be y equals a times 1.20 to the t. If I was decreasing by 20%, we're following the same structure, right? We're going to take that 100% and we're going to subtract the 20. So we're going to take the 1 minus the 0.2. So when we get our growth factor, it should look something like 1 minus 0.2, which is 0.8, right? Again, making the connection between decreasing and a number less than 1, increasing and a number greater than 1. Okay, so the percent change in both cases is 20, but if we're increasing, we're adding it to 1. If we are decreasing, we are subtracting it from 1. Okay, so let's see how this looks with word problems. Consider a savings account with compound yearly interest. You deposit $2,000 into this account that earns 5% annual interest. Can we come up with a function for this situation? Well, yes. We have an initial amount, right? The amount you deposit, the amount you put into the bank. We have a percent change, right? A rate of change as a percent. We know that when you're increasing by percentages, right, you're always taking it off the other amount. So that's how we know it's an exponential function. So y is equal to my initial amount times, are we increasing or decreasing? Well, we're increasing because interest is money that the bank pays you to put your money with them, okay? You're always looking for accounts with interest. That's how you make money, by putting it into the bank. 5% as a decimal, just so you remember. We move over 2 decimal places, so that's 0.05 to the t. And typically we simplify it, so that's 1.05 to the t. Okay, that's a rule. How much money will we have in our account at the end of 5 years? Well, I'm going to plug it in. T, in this case, right, it's annual interest, so my T is in years. So I can just plug in 5 directly into my exponent. And when I do so, I get the amount 2552.56. So if I get $2,000 for, I don't know, graduation, and I put it into a savings account that gives me 5% interest, without doing anything to that money, in 5 years, when I'm done with college and I want to pay off some loans, I would have $500 extra in my account that wasn't there, that accrued over time periods. Okay, so when you're banking, exponential functions, growth, decay, are incredibly important in the real world. It's probably one of the most applicable topics that we have covered this year. And that's because banks use it all the time. Interest, right? It's used in the medical field all the time. It's used with population, right? This year's a census year. All of this stuff uses exponential growth and decay to make judgments about a given situation. Okay. So let's check one more. Consider a patient who takes 100 milligrams of medication, right? An Advil. Once it is taken, the body filters out 15% of the medication from the bloodstream every hour. Can we come up with a function for the situation? Well, yes. We are given a percent, okay, and we're told it filters out. That means we are decreasing, right? And that should make sense. If you take medicine over time, it wears off. So we're decreasing. We have an initial amount of 100 milligrams, okay? And the time, the time in which it changes is hourly, okay? So my time in this case will be hours. So what's my function? Well, y is equal to my initial amount times 1 minus 0.15 to the t in hours. This simplifies to 100 times 0.85 to the t. How much medication will the patient have in their system after 3 hours? Okay, so hours matches with hours, so we can plug it directly in. And we have 61.41 milligrams left in our system. Okay, so we still have a significant amount of the medicine in our system. So you probably would not take a second dosage after this time. Okay, if there's any questions, feel free to email me, and I have no problems answering. Have a great day.